Thank you very much for shedding light on the investment in energy and aluminium. The next speaker is Hjálmar Gíslason, and he's going to show us the results of his recent digging into the available data that he so cleverly is extracting from obscure documents in Iceland. Just a couple of minutes to get this computer connected. Okay, Hjálmar, the floor is yours.
Thank you. I'm going to be presenting some data on the Iceland and energy. I should say first of all that I'm not an energy expert. I consider myself, however, a data expert, and what I'm doing is similar things that I've done with a couple of other topics, where I've kind of taken a layman's view from the standpoint of the topic and dug into some public data and tried to put them in light. So we leave it to others to criticize the actual data. First of all, we're going to be talking a lot about units, and we're going to be talking about watts. Watt is an energy or a unit of power, and 100 watts is roughly the same amount of power as you produce when you're driving a bicycle. Average man is driving a bicycle at 25 kilometers per hour. It also happens to be a similar power as is used to power my laptop at this moment. So a kilowatt is an equivalent of 10 average people cycling at about 25 kilometers an hour. A kilowatt, so 10 people riding a bike for an hour would equal a kilowatt hour. And kilowatt hour is a unit of energy, and we're going to see a lot of kilowatt hours, a lot of other watt hours. So I'm going to go briefly through that. We have a megawatt hour, which is 1,000 kilowatt hours. We have a gigawatt hour, which is 1,000 megawatt hours. And we have a terawatt hour. We're going to be talking about several of them. And the terawatt hour is equivalent to 10 billion people cycling for 1 hour. Or roughly the entire population of the Earth cycling for 1.5 hours. So it's a lot of energy. In Iceland we have less. We have a population of about 320,000 people. We have an area of about 103,000 square kilometers. And we have a total energy, I'll come back to this. We have a total energy of 548 terawatt hours per year. So it's a new unit. A terawatt hour per year means how much energy can we produce, or is possible to produce per year, or consume. So energy per person is 1.7 gigawatt hours per year per person. It's an equivalent to each and every one of us in Iceland to be able to have 17 million people cycle for 1 hour with us. But before we get carried away, let's look at the nature of this energy. Energy comes from two directions, so to speak. From below, in the form of geothermal energy, here nicely captured in this area, and from above, in the form of rainfall, which then every raindrop has to flow into the ocean through some stream, and that can be captured in other forms. So this is actually, this is when they were testing the bottom outlet of the Karlsruhe Dam just before they actually captured this energy. So a lot of energy there. But let's not get carried away, as I said. The number that I was talking about before is the total energy that actually arrives in Iceland. This means that every raindrop that falls on the island and every little piece of warmth that comes from below on the land surface. And these images that I didn't want to translate in kind of because of integrity, they basically show what happens with this energy. So the 548 terawatt hours a year are here. They go through various processes of kind of devaluation, and we end up with 59 terawatt hours per year through geothermal and 64 terawatt hours per year in potentially usable energy. Again, we should not get carried away. This is still a very big number. But this would mean that every little creek and every little hot spring in Iceland would have been harnessed. So the number that is usually talked about is somewhere between 45 and 60 terawatt hours per year. 50 is a common number. So it still means that each and every one of us could have the entire population of Copenhagen cycle for an hour. We probably love that. The two types of energy are a bit different from each other. Water is quite efficiently turned into electricity with the stored energy that comes that lies in water in a certain height, transformed into electricity, but it can be turned into a lot of other energy. Geothermal, on the other hand, is quite inefficiently turned to electricity, and we use it for a lot of other things. Only when we produce electricity with geothermal, only about 10% of the actual energy is used. But this shows in comparison the other uses that we have. So, in fact, a lot more than goes to creating electricity goes to heating our houses, because most houses in Iceland that we know are heated with geothermal energy. Other uses include fish farming, snow melting, swimming pools, etc. So again, we're really blessed. So now a little bit of history. This shows electricity generation in Iceland since 1920. So these are the years, and these are actually the gigawatt hours. So it goes from 0 to 14,000 gigawatt hours on the scale. And I'll quickly kind of show you the records, power plant records that have been made in Iceland. We started already with a capacity of 1 megawatt in 1921. We go to Hjálmar, 9 megawatts, now produces 50 and is still operating. Irakos with 30, now at 48. Fullfed, 120, now 270. And in the same year, we start turning geothermal energy into electricity with Hjálmar. Very small one, 3 megawatts, but it's the start. Yeah, I forgot to mention, the blue is hydroelectricity, the red is geothermal electricity, and the small spot that you see here is electricity generated with fuel. So just to mention that. So next we have Hjálmar, 210 megawatts, still our second largest hydro plant. Nesjavellir, 60 megawatts, now has been increased to 120 megawatts. Reykjanes, which was when it started 100 megawatts, still is, and was larger than that one. Nesjavellir was started, then finally with Kárahnjúkar with a capacity of 690 megawatts. By far the biggest power plant that we have locally. So, this is a nice history. Who actually uses this electricity? Let's change the image a bit. So now, blue shows ordinary consumption of electricity, and the red shows consumption by power-intensive industries. These were not split up before 1960. Doesn't really matter. We see how it develops there. And if we look at a few points here, I choose a few years random. 1970, ordinary consumption, the blue part, the part that goes for every home, every school, every little small business, everything other than power-intensive industries, was 48.3%. This ratio was kept similar for 20 years.